This is R1, R2, R0. Okay, and so what we know up to now is that we found this boundary point, and for at least for a class of channels, well, in fact, more than that. So I mean, actually, for deterministic broadcast channels, we actually found the entire region. We didn't look at the common rate there, I suppose, but in any case, this boundary we found when the common rate was 0. But for the deterministic case, we could find the whole region, although it's a little bit more of a sophisticated expression than the one I showed you. Okay, and part of the problem here is that the coding method we used in this common message, not their case, is that we're actually missing one fundamental approach to communicating, and that's what the superposition coding is. Actually, superposition coding was invented first. I think it's also the more natural coding method than the binning. So you've already seen, or the Martin coding, so you've already seen the more difficult piece. Now to start about superposition coding, a very important method. One reason it's also important is because it's easier to implement. So to implement superposition coding with real codes, it's actually quite natural. We'll talk about that, some examples of that. But before we start, we need to cover one thing about conditional typicality. We've already covered this with the Markov lemma, so all I'm doing here is considering a little bit more of a general case than the Markov lemma. You'll remember for the Markov lemma, we had a model that looked like this. We have, when I draw this as small letters, I drew this as small letters to say, well, this means yn is typical, was produced by such a source, and we'll assume un is also produced by such a source. So with high probability, they'll both be jointly typical. And then suppose we have another channel, let's call it px given u, that produces a random sequence. And we're asking now the question, given this situation, so yn and un were two sequences produced jointly out of the source pui, so they're jointly typical with high probability. Let's say they're jointly typical. And then we produce xn out from un alone. What's the probability that these two here are jointly typical with respect to some joint distribution on pu yx. Now, last time we asked that question when puyx corresponded exactly to this experiment, in which case the probability is close to 1. Here we're asking a question, what happens if we don't test with respect to this distribution but to another one with these marginals? So the setup is like this. Suppose xn, yn, un are typical with respect to p yu. We're asking the question, what's the probability? How does the probability behave that xn is in the conditionally typical set with respect to any p yux? So not necessarily the one with the right Markov conditions. I guess I should put conditioned on yn un. And I think that is it. So that's just this thing here. Oh, no, I need one thing more. Of course, this one here is created with respect to un, so I do have to put in here conditioned on un was produced with respect to un. Otherwise, I would just be creating, if I didn't include this, then I'm basically saying xn is being created independently, right? So that's why I need this conditioning, that un was produced with respect, xn was produced with respect to un. Okay, so we had this problem last time, and because of the Markov chain, if this thing here is pu, py given u, px given u, then we're testing this probability with respect to the actual setup. That's the Markov lemma case, but now we're just testing it with respect to the general joint distribution. And it turns out that the answer here, and it's also not too hard to prove using properties of conditional typical sequences and typical sequences, this probability is approximately 2 to the minus n, the mutual information between x and y given u. In fact, it's almost obvious that it should be this. Why? We'll just reorganize the u's into, like suppose it was binary, just reorganize all the zeros together, all the ones together. Then we just have, if we just look at the zeros case, then we can effectively drop this and say, what's the probability that two sequences that were produced independently happen to be jointly typical with respect to u equals 0, right? And u equal 1, so this just becomes the average. So it should make some sense that that's what's happening. In particular, if we do inside here, this mutual information use this Markov chain, all this is 0, right? Then I, x, y given you 0, and if it's 0, we get 1 approximately. I mean, you have to be a little cautious. There's always epsilons in here, and so one proof is slightly different than the other proof because of that. But the intuition is correct, right? So if we test, if we choose this here to be this, and then compute the mutual information, then we'll get 0 here, as expected, which is the Markov lemma that we have. Okay, is that clear? So we just needed this conditional version. And that's the most sophisticated experiment we will be looking at anyway. Okay, so now we can go to superposition coding because we need that. Because what we're going to do is stack code books on top of each other. So superposition coding is a method of stacking code books. So I'll just call it that. This method is particularly useful if one of the two channels is better than the other. So the idea is as follows. What we do is we choose a joint distribution with an auxiliary random variable again, pux. And let's consider the case R2 equals 0. Okay, so we're actually going into, we're now studying this particular case. So R2 is 0, so we're in this plane here. Like, so what we're after is sort of a curve inside this plane, hopefully touching the capacity region. You'll see why. So the reason for considering R2 equals 0 is because what we're thinking of is a case where in our broadcast channel, X, Y1, Y2, one of these channels will be better than the other in a very precise sense. So suppose this is better than that, then of course anything I send to this channel I can decode here too, so I may as well consider it to be common message. So what's going to happen here is this one will decode both messages and this one will only code the one message intended for it. So that's why we're considering R2 equals 0 here. Okay? Or maybe I should have said R1 equals 0 here. So here, and I guess in this case, R2 equals 0. No, the common message will go to both. Yeah, so the common message will only go to him, but this one will decode more, the common plus extra, right? So Y1 is better than Y2. So that's the idea. Anyway, let's just consider this case. What we're going to do is first generate 2 to the nr0 code words un, w naught for w naught. Okay, so that's the ground code word via pu, right? So if I draw this, this is quite straightforward. We just have a code book un1, un2, un to the nr naught. And now what we're going to do the following. For every one of these code words, we're going to generate another code book. So for every one of these, we generate a new code book of x's. So xn with indexed by 1 and 1, xn 1 comma 2 to the nr1. And the way we're going to choose these code words is we're going to consider the conditional distribution. And for every one of these letters, so for the first letter here, we'll generate an x conditioned on that letter, generate the next x conditioned on that letter, next x conditioned on that letter, and so on. Okay? That's the construction. So next, for every code word, W naught, or every message W naught, generate 2 to the n R1 xn W naught W1 running from W1 to 1 to 2 to the n R1 by choosing xi W naught W1, so the ith letter of this code word via px given u dot given u I W naught, all I, equals 1 to n. Okay? So we're just it's again a random coding. We're using this distribution. So for this position, we use that first letter, second x, the second letter, third x, and so on. And then we just repeat that for all code words. So there's lots of code books here, right? They're all stacked on top of each other. And it's interesting to think, we'll talk a little bit later how to simplify this, because we don't, of course, want so many code words, code books, because there's an exponential number of code books here, right? There's an exponential number of code books. For every code word we have in a code book. Of course, what we're going to wind up doing is choosing these to be all the same in practice, or maybe doing some kind of randomization or something of this sort. But in any case, that's the idea. That's the code construction. Okay, and so the idea here is that U will be decoded by both receivers, and W naught, the common message, of course, is decoded by everyone. That goes also to the weak. Has basically the message for the weaker receiver, and then on top of that, we have a message that the stronger receiver can additionally decode, right? Because it's stronger. Namely, in this case, we're assuming this one's stronger. Of course, we could always do it the other way around, but do it for message 2, receiver 2 or receiver 1. Okay, and so this is the method that Tom Cover had in his 1972 paper, this coding method. And he had a nice picture in his paper from 1972. So I'll sort of redraw this, not exactly, but similar. So the idea he had was one way of thinking of this intuitively, if this is the space of all code words you're sending, what you have is the U's represent cloud centers. For example, I'll give you an example, I guess. So for example, this might be easier to see via, if we think of Gaussian or additive channel. It's like suppose x was, we choose xn to be un plus vn, where vn is some additional code words, then the UNs here, so the base code words represent cloud centers, so this might be like UN1, UN2. These are far apart in this big space because we're not going to choose too many of them, and so on. And then the V's will be, these might be like a higher powered signal, and then here we'll have a lot of low power signals, which act kind of like satellites around these cloud centers. Right, so these are all the V's. VN2, 1, VN2, 2, and so on. Right, so that's one way of thinking of it. And in fact, when you do modulation, like 16 QAM, you can think of this. So, for instance, 16 QAM, you know that in communications, you often send using 16 points. You can think of this as being 4 points, being the 4 quadrants. And then around those, you add another QPSK signal set on top of each of those with less power, right? Well, the white part is just the U. 2 bits are there, and another 2 bits are in the green in the purple part. And a weak receiver might only be able to tell if you're in one of the 4 quadrants, and a good receiver will be able to get all points, right? So it's the same idea. same kind of principle. I'll point out a few subtleties in this versus this thinking, but that's what we're going to look at. They're subtly different, and you might not see it right now, but I'll point out what the difference is. But that's the fundamental idea behind this. That's superposition coding. And these kinds of things have been reinvented many times in the communications literature. Like sometimes you see, oh, we're going to, I mean, it's effectively doing something like multi-level coding, multi-stage decoding. It's the same idea. Multi-level coding is superposition coding in sort of the information theory language. Okay? So, but this is the formal construction. And now, of course, we want to talk again, how does the encoder work? Well, anyway, so I should have said cloud centers. And around every cloud, there, you know, the set of V's, so that's the value, the V's will be the guy, well, it's these guys, it's not really the X's, but anyway, the set of V's, the X's are these guys anyway, this is the cloud. So if you look in Tom Kober's paper, you'll see a picture like this. Okay? It's an intuitive picture. Okay, how does encoding work? That's easy, right? Given W naught W1, send xn W naught W1. So you see that U doesn't even play a role in the actual transmission, right? So where is U? It's nowhere. We're never choosing a U, but of course effectively U is there because it serves as the basis for which all these X's were generated. So it's kind of underneath. So it doesn't appear anywhere explicitly, but that's how these X's were designed. Like the X's won't be uniform over all space anymore because of this construction. They'll all be sort of centered around these balls. And that already tells you maybe this isn't always the most efficient method, right? Because somehow the code words aren't really uniformly distributed over space here. They're sort of, you know, surrounding balls. This sort of geometric intuition, you know, maybe it'll lead one day to an improvement of this method, because if you think of what Martin coding is, that's very uniform in space, right? There's nothing like this happening there. This construction doesn't feel like the code words are properly spread in space if you look at the geometric picture. So maybe there's something that works in between, I don't know. Because the best coding method that's known just takes this method and it stacks. It does a basic code book and then stacks the Martin coding on top of that. That's the most general rate region known for the broadcast channel today. And again, there's a little bit of a weakness, because if you think of that geometrically, we're basically having binning and cloud centers all over the place, right? So it's still not uniformly distributed code words. So maybe there's a way of fixing that. I don't know. Nobody's ever suggested something like that. That's precise and, you know, where you can show something. But maybe there's a way to fix this. I've always thought about it from this perspective. Okay, so, but I hope you understand the intuition anyway. I don't know if that's possible. Okay, so let's talk about decoder 1. What does decoder? So this is straightforward. Decoder 1, well, everything here is now straightforward. There's nothing really new. So given y1n, decoder 1 is going to try to decode both, because we're assuming it has to, right? Find w naught tilde w1 tilde such that the triple un w naught tilde x n w naught tilde w1 tilde y1n is jointly typical with respect to pu xy. And you'll see here in the decoding the u has appeared again. You might be tempted to not include this, right? You might be tempted to just say, well, we'll just find xn, that's jointly typical. Okay, but we want to include the u here. Okay, so that's decoder 1. And decoder 2 is similar, except of course decoder 2 is just trying to decode the common message. So the only typicality test it will do is with u and not with both u and x, right? Decoder 2. Of course, if you're successful, put out the estimates. If unsuccessful, put out a default message. Similar, but the decoding test is un w naught hat. I'm just choosing something other than tilde, so is element of t epsilon n pu y2. This should be y1, pu y2. Okay, it's clear. So of course he shouldn't bother trying to decode the first one, he doesn't want to. By the way, I mean, all these decoders are of course suboptimal. Maximum likelihood decoding is best, but it's harder to analyze. That's why we do typical sequence decoding, not because I don't think anyone has ever built a typical sequence decoder. I don't know if anyone ever will. It makes no sense practically, but it's a theory tool. I sometimes say that because I've run into students who've always only taken information theory from Cover-Thomas, and then sometimes they ask questions where you really realize, wait a minute, they think that people actually build typical sequence decoders because that's all they've ever seen. And no, we don't build typical sequence decoders. But they're an extremely useful tool. Okay, so analysis. Error analysis. Well, let's start with the second decoder first. That one's a little bit easier. That one's kind of straightforward, right? I mean, for the actual transmitted message, U is typical with Y2. Why? Because U is typical with X, because X was stacked on U, and then we sent the X and Y2 came out of the channel. So these two are correct. For the actual transmitted W0, we get typical. For those that weren't transmitted, we get, and the probability that they're jointly typical is 2 to the minus n IU Y2, and then we use the union bound. So here it's kind of straightforward. R2 better be, R0 has to be better than, less than IU Y2, right? That comes out of exactly the usual analysis. So there's nothing new there. Now with decoder 1 there is something slightly new, and the reason is because there's two messages in here, W0 and W1, so we can have different kinds of errors happening, and we have to study every error event separately. So for decoder 1, there are three distinct error events that we want to study. One is that one type of mistake we can make is that W naught tilde is not equal to W naught, and the other one is W1 tilde happens to be equal to W1, right? That could happen. It could happen that our decoder will put out the correct W1 but the incorrect W0. Okay, so let's study that. What's the probability that something like this happens? Well, that's going to be upper bounded by, so the probability of this event, let me call it P1, is going to be, what's this event? It's the union over all W0 tilde not equal to W0 of the event that this happens to be typical, right? UN. So let me write, what I'm going to do is I'm going to write in large those things that should be independent, because W0 tilde here isn't the correct W0. What about X? Is X going to be independent of the output? Well, yes, because I have the incorrect W0 in here. So it's a different code word that was generated independently, and it isn't dependent on U either, right? Because the U is different. So in fact, I can write this as big too. So even though the W1 is correct, because the base value is different, we're in a completely different code book. We're in the right column, but we're in a completely different code book, right, of all those code books. So it is independent of Y1n. And that has to, so for us to make an error, this has to happen to be typical with this, right? Okay, that's that error probability. Now we just use union bound, and it's very easy. Here we're just going to get R0 has to be less than, right? We have 2 to the n R0 less than. What's the probability that is typical? Well, that's just the mutual information between U, X, and Y. 1. Right? That's the bound we'll get. Okay, is that clear? Okay, and of course we'll get the same bound if both are wrong, except then we'll have to take a union over a larger set. Right, so let's consider the second case. That one's easy. W naught tilde not equal to W naught and W1 tilde not equal to W1. Well, now we have to do a union over both incorrect W naught and incorrect W1, but we get the same independence across both because now this one doesn't happen to be in the right column. How many values are we going to get here? Approximately R naught plus R1. It's actually 2 to the n R naught minus 1, right? 2 to the n R naught minus 1 times 2 to the n R1 minus 1, but that's pretty close to 2 to the n R naught plus R1. So the bound we'll get is the same bound as here, but R naught plus R1 less than IU x y1. And of course now we see this is redundant, this bound, so we don't need this bound. That's redundant, right? Because this bound is tighter than that bound. Okay, there are different error events, but there's still one bound. There's just many more. There's many more of these events than these, exponentially many more. Okay, so that leaves us one final error event we have to study, namely that the base message is correct, right? W naught tilde is equal to W naught, so we're in the right code book. But W1 tilde is not equal to W1. And now the error probability, let me call that 3, the probability of the union over all W01 tilde not equal to W1 of the events that, now the U is the correct one, UN is the correct one, W0, and only the XN is different. T epsilon n p u x y1, right? And guess what we have now? Now we have exactly that situation we talked about before in that experiment, right? The statistical experiment here is exactly that u and y1 were created jointly, right? Because u is the one that was chosen and y is the one, so these are jointly typical. But the x was only chosen via u, not via y, right? And so we're back exactly in that situation we're interested in, which gives us this is less than or equal to, the union will give us 2 to the n r1 minus 1 times 2 to the minus ni of x y1 given u. That's why I needed to do that example. Okay, so the bound we get now is going to be R1 has to be less than that mutual information. Okay, and now that's it. Okay, that's what we need. Those are all the bounds we need to ensure that there exists an encoder and a decoder and two decoders such that we can make the error probability as small as we want by scaling the block length. Okay, so the achievable rate region, let me write it like this, R superposition of PUX, that's what we need to optimize, is the set of rate pairs R0, R1, such that 0 less than or equal to R0 less than or equal to I U Y 2. That's decode bound for decoder 2. 0 less than or equal to R1 less than or equal to I of X, Y, 1 given you, and R1 plus R2, R0 plus R1 less than or equal to I of X. Well, it was UX, Y1, right? But this is the same as IXY1 because there's the Markov chain UX, Y1, Y2 is Markov, right? So here I can just write XY1. And that's the rate region. So if I want to be precise, I can still add UX, Y1, Y2 are Markov. In all these expressions. So it's Markov chain. So that chain is Markov. Okay? Fine. Fine. Any questions about that? Okay, so that's the achievable region. Now we can look at this in this plane here, and what do we see? Well, so if I plot this in this plane, we have here R1, R0. We see there's a pentagon shape. So this one here is at IU, I2. This here is at IX. And so we would get this, and in sort of the interesting case, this bound here would somehow cut this. Now it could happen, and we'll see examples of this where this bound lies above in a moment. So when we talk about degraded channels, we'll see that this bound lies higher than the rectangle. But in general, we'll have this pentagon, and so this point here is then going to be IX1, IXY1, which is the same as IU XY1 minus IXY1 giving you. So this is IUY1. This here is IUY1. And this point here is IXY1 minus IUY2. And in particular, what we're going to see is if the channel to Y1 is better than the channel to Y2, this will lie above. And that's when this curve won't play a role. But in general, it does play a role, right? So this coding scheme is for any channel. It doesn't have to be for channels where one is worse than the other. We can always apply this method. And here we decided to apply it to the method without a rate too. Speaking of which, though, now it's really interesting to see the following trick. Anything that's common, I could convert to R2, right? Because user 2 has it anyway. And all it means, suppose I replace R0 by R2, I would also get a achievable region with R2. Why is that? Because user 2 is decoding that, and user 1 will just throw out those bits that it decoded, right? So in fact, I could make this a triple region very easy by converting some R0 rates to R2, and then just replacing R0 everywhere with R0 plus R2. And then I get a region that is over the entire region, right? But it's sort of a simple region. It sort of just cuts, it's kind of like having a curve here and just cutting it down, right, with the same shape always, right? Something like that is what it represents. But anyway, this is what I could do it this way. And I also get another region by flipping around the decoding. Like maybe I want user 2 to decode both and only user 1 to decode one. So there's two orders I could do this in. So I get two classes of regions through this. Okay, but do you understand that trick? I'm just converting some common bits to bits that are private, that are dedicated to user 2, and user 1 decodes those two, but then just throws them away after decoding, right? Because user 1 is decoding both of them anyway. Okay, so that's just a simple. Okay, so we'd now like to study this region a little bit more closely. First, a few, I guess, comments again. Turns out that the cardinality of U need be at most. Well, that's interesting. Here I only have the bound y plus 2. I think it can also be less than x1 times x2. I'm quite sure it can be less than x1 times x2 plus 1, but maybe it's plus 2. It's something like this. This one I'm not sure about. But the point is, for broadcast channels with finite cardinality, output alphabets and input alphabets, you can limit the search for U to be not too large. Well, depending on what not too large is. So that's one comment. And
using the same theorem that you talked about earlier.
Yeah. So this is Kara-Theodori again. Kara-Theodori. I mean, it's a geometric result. It says, let's see if I can recreate it quickly. Suppose I have a bunch of points in this two-dimensional plane, say 4 points, 5 points. And the question is, What is the... See, I want to... it's a geometric result that has to do with the convex hull of these points. So the convex hull of these points is this. All points inside, you wrap something around it. And you ask the questions, how many of the points in the original set do I need to make any point inside the convex hull a convex combination? What's the smallest number of points of the original set, which is the white point, so that I can get any point in here? And you see the answer is what? It's 3, right? Like, for instance, this point is a convex combination of this, this, and this. And any point inside the convex hull is a convex combination of 3. And that result has to do... That's Carathéodory's theorem that says that the number of points is at most the dimensionality. Here we have a 2-dimensional set. Is the dimensionality plus 1. Okay? Now, if the set is connected, so here you'll see the original set S is not connected. You have points that, there's no line going. But if it was connected, then Fenchel and Eggleston showed that you lose 1 dimension. You can reduce the number of dimensions by 1. Right? So, so for example, let's see here. Let's do a connected set. Well, this one here. There's a connected set. So once we have a connected set, the white set, now it can represent any point in the convex hull by only convex combination of 2 points, right? Rather than 3. That's the Fenchel-Eggleston strengthening in quotation marks, because it's not really a strengthening. It's a strengthening under certain condition. Eggleston strengthening. It's D, okay? And that's what I'm talking about in terms of the strengthening. So showing these cardinality bounds is purely a result of this geometric type. You can map it into something like this. And it turns out this is general. So if we have a 3-dimensional set that's connected, then the maximum number of points we need to construct any point inside the convex hull of the set, if it's connected, is just 3 in 3 dimensions, or 4 in 4 dimensions, 5 in 5 dimensions, and so on. So Carathéodory, by the way, is a very interesting person. There's a nice book about him which I read once. He was a Greek mathematician. He was one of the most famous mathematicians in the world in the around 1930, 40, also going through World War II. He worked in Munich. His final station was the university in Munich. Now I guess it's the LMU. It's the parallel university to the technical university, and he was the president of, I think, the International Mathematical Union at that time. He handed out the first Fields Medal, so he was the president of probably of this big society, of this big World Mathematician Congress or whatever it was called at that time. I don't know, but he apparently gave out the first Fields Medal. So he was on those committees at the time. I think there's an accent here. He was also very prominent, well connected in the Greek elite groups. He was sent by the Greek government to start a new university in Izmir. At that time, it was a Greek city. I forget what the name is. I should know, but it's not in my head. And then very soon, after about 3 years of building up the university, Ataturk came and took over all of all of the Greek towns in Turkey. So it's a lot of fun, or not fun taking over, but the history is interesting. The history is interesting to know. Yeah, it's a very interesting personality, a real personality, obviously. He was criticized a little bit because he wasn't very vocal about, a lot of Jewish professors lost their positions in Munich or had to leave Germany during the World War, and he wasn't pro National Socialism. He was silent, so he didn't say all that much. And later he was criticized a little bit for that, but okay. More historical comments. Fine, so let's go to degraded channels, since that's one thing we wanted to do in this hour. So what is a degraded channel? And that's this kind of class of channels which are interesting. Though quite a few practical channels are degraded. Degraded means one channel is better than the other. So you can just think of the case where you have a base station, one person is closer to the base station, one is further away. So that's natural to think everything the closer person can decode, further person can decode, so can the closer person, right? So let's talk about that. Degraded broadcast channel, because it'll turn out to get the capacity region. It's the capacity achieving coding scheme for degraded broadcast channels. Okay. So there's two classes of degradation that I want to talk about. One class is called physically degraded. And what that means is that the chain X, Y1, Y2 is Markov. Okay, that's what it means. And you can, the reason for calling it physical is in some sense it has to do with thinking about, Y2 is a noisy version of Y1, which is a noisy version of X. So there's some kind of physical thing here. So for example, suppose that, suppose we have a Gaussian channel or an additive channel, and Y is X plus Z1, and Y2 is Y1 plus Z, I don't want to call it 2, so let me just call it 1, 2. Okay? That's an example of where you have a Markov chain. Now, when you look at that model, you say, well, that's not how real broadcast channels would look like. If I was naturally thinking about it, I would guess Y2 should be equal to X plus Z2, where Z2 is statistically independent of Z1, right? And that doesn't fit this chain. And it doesn't fit the chain. However, it turns out that this channel has the same marginals as a channel that looks like this, and so we know the capacity regions are the same. So we may as well study this channel to understand the capacity region and even to understand what coding schemes to use, because we know the error probability of a decoder for both situations will be identical. So the design even of the decoding and coding is identical whether we have this case or the case we're interested in. And that's the usefulness of this observation, that the capacity region of the broadcast channel depends only on the marginals, which was already in Tom Cover's original paper. Okay, so this lets us define a second class of channels. Well, let me leave it here. Namely, stochastically degraded channels, or sometimes they're just called degraded channels. So this is the more general class. Stochastically degraded. What it says is any channel is stochastically degraded, so Py1, Y2 given X is degraded if it has the same marginals as a physically degraded broadcast channel. If it has the same marginals as a physically degraded channel. Py1, Y2, let's say given X. And of course, if this is physically degraded, then we can write it as P of Y1 given X, P Y2 given Y1. Right? For some Py2 given Y1. So if the marginals of both, so if a channel has another, has the same marginals as some physically degraded channel, we call it stochastically degraded. For example, this channel here has the same marginals as the channel, the broadcast channel X plus Z1, which is the same, and Y2 tilde is equal to Y1 plus Z. I should be careful. If the variance of Z2 is bigger than the variance of Z1, then we can find another. So what we're looking at is Z1 is normal, zero mean, power sigma 1 squared. Z2 is sigma 2 squared, and we're assuming that sigma 1 squared is less than sigma 2 squared or equal to. And then this one here can have variance sigma 2 squared minus sigma 1 squared, right? And then both channels have the same marginal. So in fact, we may as well study this channel to compute capacity region and also to develop coding schemes. Okay, is it clear what the trick is? That's the idea. Okay, and the Markov chains are very useful because they're conditional statistical independence, and that helps us do things like bounds and so on. All right. So let's take a look. What happens to this region if we have a degraded channel? Okay, it's in the right order. So of course you can be degraded either way, right? User 1 is better than user 2, or it could be user 2, user 1. It's natural also that if you're degraded this way, that user 1 decodes both things, right? Because anything user 2 can decode for sure, user 1 can decode. At least that's what makes sense. We can check this now formally by seeing what happens to this rate region when we have physical degradation. So let's take a look here. Let's look at this. Let's look at the sum of these two bounds. If I add these two bounds up, this one plus this one, I get the following bound. Adding the first two bounds. What do I get? Well, I'll just gonna get R0 plus R1 plus R2. It has to be clearly less than the sum of these two. But this thing here is less than or equal to IUY1, right? Just by the data processing inequality, right? By the data processing, that's smaller. And this, so this whole thing has to be less than or equal to IXY1, right? Which tells me this bound is redundant, right? So I may as well throw it away. So for these channels, I just get these two bounds, and that's exactly the case where this diagonal bound is higher than just the rectangle. So in fact, rather than getting a union of pentagons, I may as well just consider a union of rectangles. Right? That's what it looks like. And now I have to take, I'm going to get many rectangles. For every choice of PUX, I'm going to get a different rectangle. So we'll see examples of this happening. And then we might get a region that looks like this, based just on the corner points of the rectangles, right? So this will be the union, this is the union over all PUX of R PUX. Now, for degraded channels. So for degraded channels, this turns out to be achievable. And what we want to prove is that this is actually the capacity region of any physically degraded broadcast channel, and therefore also of any stochastically degraded broadcast channel, including our Gaussian scalar broadcast channel here. Okay, so that's the nice result. Superposition coding is optimal for degraded broadcast channels. What about Martin coding? Is that optimal? It turns out in general, no. You won't get as large a region. For Gaussian cases, we'll see the answer is yes, but that's because of this special Gelfand-Pinsker result for Gaussian channels where you can get rid of interference. So there's a lot of things to keep organized in your head, but in any case. Okay, so let's do some examples. I guess that's next. Yeah, so it's the Gaussian channel. Well, no. Well, let's first do the other one. Still have 5 minutes, so let's do for this hour. So let's first do, well, we could go right to the Gaussian case, I guess. Then we'll do the binary symmetric case after that, I think. Or maybe not. Let's do the converse. That way we get it out of the way. So let's do the converse. So the claim here is that this is the capacity region. So the claim here is that the capacity region for a degraded broadcast channel is the union of PUX, where UX, Y1, well, Y1, Y2 is a Markov chain of R of PUX. That's the claim. So now we have to prove an outer bound that matches that, and that's not too hard to do for this channel. And we want to do it, of course, for the stochastically degraded case, but no, we can do it for, we know we can do it for the physically degraded case, so that's going to help our converse too. So let's do it for the physically degraded case, since we know the capacity regions are the same anyway. Okay, so let's start with the first bound. The hard part here is going to be trying to find the same auxiliary random variable for both bounds. That's the part that's tricky, and that's usually the tricky part. But let's do the converse. Okay, again, start for reliable communication to get rid of these Fano inequality epsilons. Communication, we must have the following: n r0 plus r2 is less than or equal to the joint mutual information between w0, w2 and the estimates at receiver 2 or y2n, right? Because user 2 wants to decode both of these, right? Both the common as well as the dedicated message to it. Okay, now here we just apply chain rule, so actually absolutely nothing special. This is just summation from I equals 1 to n of I, but let me do it in this form. y2i given y2i minus 1, right? Let's just chain rule for mutual information. And this thing here is less than or equal to if I put that up front. That's easy to see. Just use the chain rule, right? And this, in turn, if I plug in y1, I get something even bigger, right? And in fact, note that this is a noisier version of that, so I can just drop this. Okay, to see that formally, just use the chain rule. y2i minus 1, y2i given w0, w2, y1i minus 1. And since this is just a noisy version of this, we could just drop that. This is 0. Right? Because y2 is just an independent noisy version of that. So conditioned on it, it's independent of anything else that goes on the network. Right? This is just, here I just have to put in, this is equal to this just being the noise, that extra z2 tilde that I added, which is independent of everything else. So it's 0. So, and that's what we need, and this is what I'm going to call my u1i. So what we have now is the following bound in general for stochastically degraded broadcast channels. y1i minus 1. And this, we'll give this a name. This is going to be my ui. Okay, that's like my u. Okay, and now after this I can say, aha, that means, you know, continuing this. This is the same as, I can now add a time sharing random variable, so let me do that. So this whole thing is less than or equal to I of ut y2t given t, where t is the same time sharing random variable we had before, times n. And now I'll pull the t up front. Okay, and now I'll just call this my u. This is my u. And this I'll just rename this my y2. Okay, and it's easy to check that if you look at what this u is. So remember what ut was? Ut is w0, w1, y1, t minus 1. It's easy to check that ut, t, ut, x, y1, y2 still forms a Markov chain. right? So it has the right form that we need. So this gives me the bound I want, the first one. And now I have to do this bound by hopefully getting the same u. I have to reconstruct the same u in that bound. And here it's easy. That's why I needed to switch from y1 to y2. You'll see. So let's just do it quickly. The r1, nr1, chalk is a little bit harder than this chalk. nr1 is less than, for reliable communications, I of w1 y1n. Okay, now that's going to be less than or equal to I of w1 y1n w0 w2. But these two messages are independent of that one, so we get I of w1 y1n given w0 w2, and now it's just chain rule. I guess I could use, yeah, I may as well just do it. W0 y1i given ui, right? Namely w0 w2 y1i minus 1. That's just that my ui. This here is my ui. And this thing here is less than or equal to I of x I y1i ui. Okay, and it's the same one, and so this here is equal to n times I of xt y1t given utt. So here's my u, right? Utt is my u, and I'm done by just renaming this x and renaming this y1, right? So I get this bound. So of course, I can still take the union over all joint distributions of ux. This here is valid for any given code book. I'll be able to find some such u, right? For any code design, I find some such u, and now I still have to optimize, just like here, over all joint distributions to get the outer bound. Okay, so that's how outer bounds usually work. You know, very often we have auxiliary random variables showing up in achievable regions, and then we have to try to find for the converse bounds the corresponding u's. Sometimes that's possible, sometimes that's not, right? So that there's a lot, the creativity in generating converse bounds, usually the hardest part of this is finding things that match, and sometimes you can't. And in those cases, we still don't know what the capacity is. There's many examples of problems where we think we know the answer, but we haven't found converses because we can't match the auxiliaries. So there's quite a few examples of those. So if you could find them, you would solve the problem. And, you know, Getz can write a paper on that topic, of course. All right, so that proves that this is the capacity region of degraded broadcast channels. And after the next hour, we'll do some examples with Gaussian channels, scalar, binary symmetric broadcast channels, and then we'll talk a little bit about vector Gaussian broadcast channels, and we'll see how far I get. If I have time, I'll also just I'll probably mention the full Martin region, and I think that for today then we won't quite get to the multiple access introduction, but we can do that tomorrow anyway, right? So good, if no questions, then we'll go break and start again in a half hour.